Hello, calculus fans. We can use vector integrals to recover position functions whenever velocity or acceleration functions are known. And this is actually something that we did in Calculus 1, just without the context of vectors. So as an example, let's suppose that we have a moving object. We know its initial position is the vector 1, 2, 4. We know that its initial velocity is 1, minus 2, 3. And let's say that we have its acceleration function. A of t is equal to 4ti plus j minus t squared k. Let's find its position at time t. Now we know that the acceleration is equal to the derivative of the velocity. So in order to get the velocity function, we integrate the acceleration function. And when we do that, we end up with the expression that looks like 2t squared I plus tj minus a third t cubed k. And now here's the important part that's a little bit different than what you're used to. Whenever you evaluate an indefinite integral, or that is, you compute an antiderivative, there's a constant of integration. However, here we're integrating vector functions, so the constant of integration that we get is a vector constant. You see how that c has an arrow on it to indicate that it's a vector. Now let's try to figure out the value of the constant vector c. We're going to use the fact that we know the initial velocity, and we also know that v of 0 is equal to c. If you go back to the expression that we came up with for the velocity function, if you plug in 0, you'll just get c. Most of everything else will disappear. So that tells us that our arbitrary constant c is the vector I minus 2j plus 3k. All right, so we take this value of c that we came up with and we put it back into our original expression for the velocity function. Here you can see that c being put in here. And then we combine like terms. And when I say combine like terms, I mean via I, j, and k. And we get this as our final expression for the velocity function. All right, next, the velocity is the derivative of the position. So now what we do is we integrate the velocity function. All right, so these are not particularly difficult integrals to compute. Notice at the end, the key thing is that we have an arbitrary constant vector. And I'm going to use a d this time because we already used c. Now we know that r of 0 is equal to d. So that tells us what d is. It's the vector I plus 2j plus 4k. Because we're given this vector right here as being the initial position. Therefore, put all this together, we get an expression now for the position vector. And again, you'll notice that here is the arbitrary vector d that we computed on the outside, and then the final expression, we've just sort of combined like terms on I, j, and k to get this final expression. Okay, that's all for now.